Hi, let's take a look at a general projectile motion problem where we can look at information in the x and y directions separately. So, a lot of baseball games over the last few years have been giving more telemetric data about what's happening. And one of the new tools that broadcasters have in their arsenal is reporting exit velocities and bat speeds for baseballs and launch angles, particularly when a ball is hit particularly deep. So let's take a look at some starting numbers and predict what's going to happen. So I have a baseball player that's hitting a ball at an angle of 27 degrees where the speed leaving the bat is 104 miles per hour. And most players, particularly when they're trying to drive the ball and hit for power, have a bit of an uppercut swing. So let's say that the ball makes contact with the bat kind of low, about 0.3 meters, 30 centimeters above the ground. Now, given that information, let's say that the ball is hit to a wall that's 20 feet tall and 390 feet away from home plate. And we're going to ignore the effect of air resistance here. So without that, is the ball going to be able to clear the fence? Well, if we take a look at this situation, we could try to parameterize things and come up with equations of motion for looking at our height as a function of x. I like personally to use the intermediate variable of solving for time, particularly when you know the information that you're working with in the x direction, because in the x direction, the only equation of motion is our distance we travel is equal to our speed in the x direction divided by time. So if we know our velocity in the x direction, so here, given our initial speed and our launch angle, our velocity in the x direction would be, well, we'd first want to convert 104 miles per hour to meters per second. So there's 1,609 meters per mile. There are 3,600 seconds per hour. So that means that there's 46.5 meters per second for 104 miles per hour. Now, our x component is adjacent to our launch angle of 27 degrees, so 46.5 meters per second times the cosine of 27 degrees means the ball is traveling downfield with a speed of 41.4 meters per second. And without air resistance, that speed wouldn't be changing. Now, 390 feet is 118.9 meters, so the time is going to be our distance, 118.9 meters, divided by our speed of 41.4 meters per second. So that means the ball will reach the fence without air resistance after 2.87 seconds. Now, the question is, what will be the elevation of the ball above the ground? Because we only have 0.3 meters to work with. If we get a height of negative 0.3 meters, that means that the ball is landed somewhere. If we get a height that's like super negative, that means the ball's hitting the ground long before it even gets to this distance. So let's see what happens. So if we look at our y direction, our initial velocity in the y direction is going to be our speed of 46.5 meters per second times the sine of 27 degrees. So that means that the ball is going to be traveling with an initial speed in the y direction of 21.1 meters per second. And it's traveling for a time of 2.87 seconds, so my change in y is my initial speed in the y direction times time minus 1/2 times the strength of gravity times time squared. Plugging in to my equation, I get a little bit over 60 meters for this first term. For the second term, 1/2 times 9.8 meters per second squared times 2.87 seconds quantity squared. That gives me about 40. And 60 minus 40 gives me, if I calculate things out carefully to several digits, 20.23 meters as my change in y. It's positive, which means it's above where it started, so the final height would be 20.53 meters. So without air resistance, this is what a baseball announcer would call a no doubt about it home run. Because it's clearing this fence. 20 feet is 6.1 meters. So if that's 6.1 meters to scale there, then 20 meters means that we're way up here, way off screen. So, towering home run. Now, with air resistance, that's going to bring in the ultimate distance it'll travel. And what it'll also do is, instead of having a symmetric parabolic shape, because we're continuously slowing down, the maximum height isn't as high, and it starts arcing and curving down faster as we keep losing that forward motion. But an angle of 27 degrees and a bat speed of 104 miles per hour are probably going to send most baseballs out of a ballpark, except when you have incredibly stiff headwinds or incredibly high walls. Thanks for watching.